Yep. All right. Well, let's finish up diagonalization today. This is our last topic that we'll talk about. So we started briefly what's going on with diagonalization last time, where we're looking for a way to write a given matrix as a diagonal matrix with a matrix and an inverse on either side. Uh, and the whole idea behind this is so that we can do computations a little bit more simply. In particular, we talked right at the end of class last time that if I look at powers of a matrix, I can replace the powers of the matrix with the powers of the diagonal matrix. If I can do this, pardon me, so that if we need to do repeated matrix multiplication, I could just do repeated matrix multiplication with a diagonal, which is much simpler because all I have to do is just do powers of the entries on the diagonal each time. And there are applications in what we refer to as discrete dynamical systems where you want to do higher and higher powers of a matrix. Like I mentioned before, if you've got anything with Markov chains in another class, for example, that's an idea of being able to do repeated multiplications over and over and over again to be able to see what's going on in the long term. So that's where we're headed with, well, that's where this stuff is headed. We're not going to do that. We're just going to talk about how we get the diagonals, but just to let you know about why we care about it. So the example we did right at the end of class last time, we showed that we had this diagonalization here for A, that if I take my P inverse times A times P, I get a diagonal matrix here. All right. Let's say we moved that P inverse back over to the other side. So this was the P inverse matrix here. All right. So if I move it back to the other side, it really was just multiplying by P. So if I start here, here was my A. Oops, that's not negative. Here's my P. And then this would be P. And this would be my D here. All right, so basically what I have set up here is AP equals PD. Okay. Let's see what happens when we do the multiplication on the left-hand side and on the right-hand side here. So if we do the multiplication on the left-hand side, notice that when you do your first, let's do it by columns here. When you do your first column, I would take this row times that column. I would have 33 minus 36. I would get negative 3 here. Right? When I do do this row times that column, I would have 9 minus 10. I'd have a negative 1 here. Right? Now, I did this as a column here because that is basically we took this matrix and multiplied it by that column and got that column vector, right? So I did a matrix times a vector to get this vector here. Okay? Let's go over to the other side. When we did this one here, if I do this multiplication, I can think about going the other way. When I multiply on the right by a diagonal matrix, it's going to multiply by the columns by these entries, right? So basically when I do the multiplication this way, the negative 3 will get multiplied by the 1, and the negative 1 will get multiplied by the 1, and that's what's going to go in that first column, right? Basically, that first column obviously is the same because they're equal to each other, but what did we do here? This matrix was A times the column. This matrix was a scalar times the column. What relationship do we see there? That we just did in the previous section. That's an eigenvalue, eigenvector idea, right? Right? Notice that negative 3, negative 1 is an eigenvector of that matrix A associated with lambda equals 1. Okay. What's going to happen on the other side? Well, when I take negative 11 times negative 4, I get 48. Minus 36 gives me a 12 here. 44 minus 36 is not 12. It's 8. Sorry. Right? And then 12 minus 10 gives me 2 here. And then notice what happens on the other one. Again, when I multiply by this diagonal matrix, this entry negative 2 will be multiplied down this diagonal to get the second column. And I get an 8 and a 2. And I have the same relationship, don't I? We have the vector negative 4, negative 1 is an eigenvector of A associated with lambda equals negative 2. So this gives us our idea of how we're going to find our matrix P and our diagonal entry D. Okay? Sorry, not our diagonal entry, our diagonal matrix D. We're going to find the eigenvalues for A. We'll find corresponding eigenvectors to those eigenvalues and create our matrix P by making them as columns. Okay? All right. So going back up to that AP equals PD idea, and then I'll answer this question here in a second. If I go back to this AP equals PD idea, if I make eigenvalues and eigenvectors, so if V1 out to Vn are eigenvectors associated with lambda 1, lambda 2 out to lambda n, then we're going to let P equal the matrix V1, V2 out to Vn, and D be the matrix lambda 1, lambda 2, lambda n down the diagonal. That should be a lambda n. That was an ugly lambda n. So that when you have AP equals, and when I have AP, that would be A times V1 in the first column, A times V2 in the second column, all the way down to A times Vn in the last column. Because again, when I multiply matrix times P, I can think of it as a matrix times the first column, write it as the first column. Matrix times the second column, write it as the second column, and all the way across. If I have eigenvectors, we know we can replace the matrix multiplication with the scalar multiplication. So it takes out the matrix multiplication, puts in the scalar multiplication. And then these should be lambda 1, lambda 2, lambda n. And then we can pull out those scalars on the right since they're all multiplied on the columns. And so we have lambda 1, lambda 2, lambda n down the diagonal. Okay. So this is how we're going to create our P and our D. But remember, for being diagonalizable, I need to make sure that my P is invertible, right? Because I want A equals PD, P inverse. If it's diagonalizable, I want to take advantage of the fact that I can do powers of diagonal matrices quickly, right? I can only take advantage of that if I can move this P to the other side, on the right-hand side. So I need the P to be invertible. What needs to be true, then, about your columns What needs to be true about the columns of your matrix for any matrix? What needs to be true about the columns in order for the matrix to be invertible? I need to have a pivot in every column when I row reduce, right? And that's another way to check what about a set of vectors. If I take it, put it in the matrix and row reduce it, and I get a pivot in every column, what does that check for those that set? 1-to-1s for transformations, I agree with that. Linearly independent, right? Yeah, it's a linearly independent set of vectors, right? So in order to diagonalize the matrix, we need to have, we can find, the answer, the end of the sentence is we can find n linearly independent eigenvectors. Okay. Now, we can't always do that. There will be matrices that you cannot do that for. Okay. We'll talk about how you know whether or not you can do it here in a minute. Okay. But this is what you need. You have to have n linearly independent eigenvectors in order to diagonalize. Now, you can always write AP equals PD whether or not they're linearly independent. You need the linearly independent part to be able to invert the P. Okay. All right. So let's look at a specific example here. Let's look at this matrix here that we have at the bottom of the page. Let's use technology here to help us find the eigenvalues and eigenvectors. Okay. So let me go to the matrix here. Let me edit A. It's a 3 by 3. No, 3 by 3. Just typing in the matrix here. All right. So just typing in my A. I need first to find the eigenvalues, right? Remember again, to find eigenvalues, we have to solve the characteristic equation. Right? We have to solve that characteristic equation. I'm going to use the calculator to help me out with that, rather than trying to do it by hand. Okay?
So on the homework it had determinant of eigenvalues of I minus A, so it doesn't matter which way it goes.
Doesn't matter which way it goes. Yeah. The reason why it doesn't matter, what's the difference between those two expressions?
And the eigenvalue is negative.
Yeah, it's just that this matrix is the negative of that one, right? Remember how you can pull a scalar out of a determinant? Depends on the size of the matrix, right? You can pull the scalar out, but it has to be the power. Well, it's either 1 or -1, but if I divide over by it, it's just going to go away anyway. So I get the same exact solutions. Yeah. Yeah. So it doesn't matter which way you do it. You'll always get the same eigenvalues. All right, so let's go back up here. I want to, remember, let's clear that up. Go in here and do the determinant of the matrix A minus X, I'll use that as my variable, times the 3 by 3 identity matrix, and graph it. Other software programs will just do it directly, but this is using a calculator since that's all you're going to have on the test. That's why I'm doing it this way. You won't have the software program to do it, but I don't want to spend 10 hours trying to do this determinant by hand and then refactor it. Okay. All right. Looks like it crosses at -3 and at 1 and at 2. Again, we can check to make sure that works if we use our 0 command on the calculator. I'm going to do it once. I'm not going to do it for all 3 here. Remember to use that. I went to second calculate here, right? Okay. Move your cursor to the left of where you think the 0 is, hit enter. Move it to the right of where you think it is, hit enter. Put it where you think it is, hit enter, and it should find it for you. Get -3, 0. Works pretty well, doesn't it? It's a lot easier than trying to do it by hand. Yep. You should be able to do the other ones with the -1 and the 2 as well. All right. So I'm going to write, I can't see it on the screen, but I'm going to write down the eigenvalues here of -3, -1, and 2. Okay. Quit out of there. I want to find the corresponding eigenvectors. So go back to my, go back here, get your reduced row echelon form of, I want to do my matrix minus, the first one was -3 times the identity. Right? I want to put in the eigenvalue and row reduce, right? Putting in the eigenvalue means that we're going to subtract the eigenvalue off the diagonal. That's what that means, right? So I'm just doing the A minus the lambda I and row reducing it. There we get that. Right? So can you tell me what an eigenvector is associated with lambda equals -3? Okay, -1/3, -2/3, 1. And if you'd prefer to not have fractions, what could you use? Yeah, just multiply the whole matrix. I know you can't see what I'm writing. I'll switch back over here in a second. Yes. Okay, so remember that we're solving a homogeneous system, right? So you row reduced to get this, but remember we have that augmented 0, 0, 0 there, right? So if you let x3 equal t, then x2 is -2/3 t, right? I have to subtract that over to the other side. This one would say x2 plus 2/3 x3 equals 0. So I have to move it over, right? That's where the negatives are coming from. I have to subtract it to the other side. Here, this one? So remember, when you're done writing your solutions, I would factor the t out. All right? I would take t times -1/3, -2/3, and 1 that way. I have to pull the t out. That's where the 1 comes from. Okay. All right. Let's go back over to the calculator here. I need to do the same thing, except that I want to change the -3 to a -1. Right? Ooh, what did I do? Oh, I hit the wrong button, apparently. All right, so then lambda equals 1, -1. What do you get for an eigenvector? Yeah, -1/3, -1/2, and a 1. And again, if I want to get rid of the fraction, you don't have to get rid of the fractions. You can use any eigenvector you want. But if I want to get rid of the fractions, I can multiply everything by 6 and get -2, -3, and 6 to clear the fractions. You do not have to, okay? You can just use any scalar multiple of an eigenvector is still an eigenvector. So I was just using a scalar to clear the fractions. No, nope. You can do a different one for each one. Yeah, you're just scaling each one individually. And then finally, the last eigenvalue we saw was a 2. So for that one, we would have a -1/2, -1/2, 1. And again, if I multiply by a 2, we'd have -1, -1, 2. Again, remember, when you do this reduced row echelon form, you have to get a row of zeros here. Have to. Don't have a choice, right? Because again, we're looking for non-trivial solutions to the homogeneous system. If you row reduce and get the identity matrix, something has gone wrong somewhere. Okay? Have to have a row of zeros, at least one row of zeros. Okay? All right. So going back, yes. Well, when you do the reduced row echelon form, the zeros are always at the bottom. All right, so going back over here, I just wrote out the answers that we already came up with, right? Okay. All right, so your matrix P then, now this is important as well. If I put it in this order, if I do -1, -2, 3 first, and then -2, -3, 6 second, and -1, -1, 2 third, then I want to make sure that my diagonal matrix, the eigenvalue in the column matches the eigenvector that I put in the column for P. Okay, so in my first column here, I'll have -3, 0, 0, because the -3 was the eigenvalue for that eigenvector -1, -2, 3. I'll put in 0, -1, 0 here, and then 0, 0, 2 here. Again, order doesn't matter as long as you're consistent, okay? Whatever order you put the P in, you put the D in the same way. Okay. Good news is you should always be able to check these, because if I put in PD, P inverse, I should get my A back again. You should always be able to check your answers when you're done. Okay? So let's do that real quick after, I know some people are still writing. Yeah.
So when you times divide x through the variable, why is it still negative? You made it positive.
What's still negative?
You times it by 3 in the top.
Yeah.
Is it not -3?
Is what not -3? The bottom one?
X3.
No, that's a positive one. I multiplied by 3. Right? Yeah. How did I get D? Do you understand how I got P? Yeah, these are the eigenvalues that are associated with those eigenvectors. This eigenvector came from that eigenvalue of -3. This eigenvector came from this eigenvalue of -1. This eigenvector came from this eigenvalue of 2. And again, the order doesn't matter. If I would have switched the columns around, you'd switch the eigenvalues around. Say that again? Yeah, it has to be a diagonal matrix. That's the whole point. Yeah, they have to be a diagonal matrix. Yeah. So let's do this real quick and check our answer. So if I do second matrix, I'm going to go down a line here. Let's put in our P. The P was -1, -2, -1, -2, -3, -1, 3, 6. Ooh, hey, I'm on the wrong key. 3, 6, 2. That was the P matrix. Okay. And then put in the D matrix here. I'll actually put it in D. Oh, if I could actually go over to the edit button. And I'm on the wrong one. There we go. -3, 0, 0, 0, -1, 0, 0, 0, 2. Now if I do my P matrix times my D matrix times the inverse of my B matrix, I should get the matrix we started with, which we do. Should get the matrix we started with. Okay. Like I said, you should always be able to check these. Hmm?
Is that going to be on the recording?
No, because it's on the other computer. It's not connected. They're not connected. Sorry. I can make a recording though of that to show you that. What's that? Yeah, I can make a recording of that. Yeah. All right. The process okay so far? We're gonna do another one. Is this okay so far? Okay. All right. Let's look at the next one. Nope, you can't see the next one. All right. Here's our next matrix. Same idea here. Let's find our eigenvalues. This one we should be able to do a little bit more by hand. We can, but I'm not going to just to save time. because I could expand along this row here to do my determinant, and it'll factor out a 3 minus lambda automatically. So it's a little bit easier to do. That one's a little bit easier to do by hand. Okay. But I'm still going to do it on the calculator to save time. All right. Let me switch back over here.
Could we row reduce also to get like a 0 in the second column, in the first column in the second row?
You can't do that because you have to do subtract your lambda off first and then your determinant. So it's a heck of a lot harder to get that to cancel out. Yeah. So it's a good thought, but when you do row operations, it'll change what the eigenvalues are. Yes.
So if I can determine like how you say like columns, just like how.
Yeah, you can do columns or rows. Yep, sure can. 6, 2, -1, -6, -1, 2, 0, 0, 3. All right, so there's our matrix. I've already got the function typed into the calculator, right? So I don't need to retype it. I would just go ahead and leave that in your y equals menu in the exam so you don't have to retype it every time. Okay, let's graph that one. Okay, it's a little hard to see. I'm going to zoom in real quick to show you what's going on there. Well, maybe it's zoomed in too far now. Yeah, a little too far. Let me move this over. Okay. All right, so notice that the graph comes down and crosses at 2, right? Came through and crossed at 2, but what happened here at 3? It just touched it, didn't it?
Yeah.
So we're getting that double root there, aren't we? So if you were to do this by hand and write out your characteristic polynomial and refactor, your characteristic polynomial would look like a 3 minus lambda squared and then times a 2 minus lambda. I know that it would be a squared because it touches, right? It doesn't cross. You get a double root. Okay. I can see that from the graph, right? So you're not going to get 3 distinct eigenvalues here. You're only going to get 2. One's repeated. Okay. So let's see what that does in your row reduction, because that might cause an issue. So let's go back over here, and you know what? I don't need to do that. I've got it stored in here somewhere. There it is. We had one eigenvalue was a 2, right? Okay. So what would the eigenvector corresponding there be? Good. -0.5, 1, 0, because my free variable now is x2, right? This says x3 equals 0. Your x2 would be t, and your x1 would be -1/2 t, right? So it's -1/2, 1, 0 for that one. Well, let's see what happens when we plug in 3, because that was the other eigenvalue we saw, right? Now, in this case, how many free variables do you see? 2. Okay, that's a good thing. Okay. All right. So we see 2 here. One of them is going to be -2/3, 1, 0, and the other one's going to be 1/3, 0, 1. Right? Because I've got a free variable. I've got a free variable here and a free variable here. Right? So you're going to have 2 eigenvectors rather than just the one. That's a good thing. Okay? In order to be able to, pardon me, in order to be able to diagonalize your matrix, we said that we needed to have as many linearly independent eigenvectors as we have columns, right? In order for the matrix to be invertible. In this case, we'll have 3 linearly independent eigenvectors. We got 1 from lambda equals 2, and we got 2 from lambda equals 3. So if I go back over here, We found those, right? Those are the eigenvectors we had. So our matrix P, again, will be put your eigenvectors in columns. Again, the order doesn't matter. And it doesn't matter if you leave fractions. I left fractions in this case. I could have multiplied the first one by 2 and the other two by 3 and got rid of the fractions. Pardon me. Order doesn't matter as long as you're consistent. The first eigenvector we put in there corresponded to an eigenvalue of 2, so the 2 will be up in the upper left-hand corner. The other two came from 3, so we'll put the 3's down the diagonal for the other two. Again, you can flip around the order as long as you flip around the eigenvalues to go with it. And it'll always work. Yes? Why do I have 2 3's? Because what eigenvalue did that one come from? No. That one came from 3, didn't it? Yep. Where did this one come from? The 3. That's why I have 2 3's. This, again, every single time, this eigenvalue has to be corresponding to that eigenvector that we stuck in that column. So it's okay that it's repeated because it came from those.
So the order doesn't matter as long as they just correspond.
As long as they correspond. Yeah, I could, if I flip-flopped those two columns, then you'd use 3 2 3. Yeah. It literally doesn't matter. You can do whatever order you want as long as you're consistent. That's all that matters. It's just one of the nice things about it, right? As long as you're consistent, you can't screw it up. All right. Okay, so that one was still diagonalizable. Let's look at the next one here. Something else must be going on. Okay. I'll go back to the definitions here in a minute, but I want to do the example first to show you what's going on. Okay. So going back over to my calculator here, let's type in this matrix C. I'm going to put it in the matrix A just because I already have it typed in the other thing, in the y equals button. 7, -4, 0, 1, 3, 0, -2, 5, 5. Okay. Making sure I typed it in right. Okay. So again, I want to find the eigenvalues first. So I'll do the exact same thing we did before. Let's graph it. I may have to zoom a different direction here depending on where it's going. Yeah, it's a little farther out. Let me zoom back to the standard window here. I may have paused it. There it goes. I did. I paused it. Notice what happened there at 5. It flattened out and then crossed, and that's it. Right? Okay.
Might as well you just stop and restart it back.
Say it again.
Might as well they stop.
And restart it again. Yeah. So this is so. What would be the power on the factor? Do you think for the lambda minus 5 piece? 3, right? Because it flattened but still crossed. So that's going to be a lambda minus your characteristic polynomial in this case. Going back over here, your usually use a p for it. Your characteristic polynomial for your lambda here will be 5 minus lambda cubed, or lambda minus 5 cubed. It doesn't really matter. You get a triple root in this case. Okay, let's go back over. Does that graph cross the x-axis, or does it just touch the x-axis at 5? Does it cross it, or does it touch it? Okay, so it crosses. It touches means it hits it and goes back up and doesn't go across, right? So crossing it, right? It crossed. So it has to have an odd power on the factor. If it crosses, it has to be odd. Since it flattened out, it can't be 1, so it has to be 3. It could be 5, but we already know it's a third degree polynomial. That's how I know it's a cubed.
If you solve and determine like the regular way, like the A minus the eigenvector, will you still get the third power?
Oh yeah. Okay. Yeah. Let's go back. Let's just do it real quick. Okay. So in this one, if you did 7 minus lambda, negative 4, 0, 1, 3 minus lambda, 0, negative 2, 5, and 5 minus lambda, that is one ugly lambda. Is that it equal to 0? Where would you expand? Yeah, this part right here, right? Okay. That 5 minus lambda would be positive because it's on the diagonal. Multiply that by 7 minus lambda, negative 4, 1, and 3 minus lambda. Right? So I'd have 5 minus lambda times 7 minus lambda times 3 minus lambda. That gives me lambda squared minus 10 lambda plus 21. And then plus a 4. So I have 5 minus lambda. Notice that's lambda squared minus 10 lambda minus plus 25. And so I'm going to get a lambda minus 5 squared there. So I'll get the same thing. Yeah. So yes, you would have got the same thing. Yeah. All right. The important part here is that we have exactly one lambda or one eigenvalue, but it's repeated 3 times, right? Remember back in college algebra class, you referred to this as the multiplicity of the root, right? For eigenvalues, this is referred to as the algebraic multiplicity. And so that's your definition of algebraic multiplicity above, okay? It's the multiplicity of the root of the polynomial, of the characteristic polynomial, I should say. Okay, that's what algebraic multiplicity is. So you learned multiplicity back in an algebra 2 or college algebra class whenever you learned about multiplicity. That was from an algebra class, so it's the algebraic multiplicity. Okay. All right. What about geometric multiplicity? Well, that comes from a different concept. So let's go back over to calculator. Our eigenvalue in this case was a 5, right? So I want to put in my 5 for my eigenvalue and row reduce. There's what you get. What is your eigenvalue, eigenvector in this case now? It's 0, 0, 1, right? Because the first one says x1 equals 0, the second one says x2 equals 0, the last one says x3 equals t, right? So you get 0, 0, 1, and that's it. That's the only eigenvector that we can find without doing scalar multiples, right? So do we have 3 linearly independent eigenvectors? No. Okay. This is what we refer to as geometric multiplicity. It's the dimension of the corresponding eigenspace. It's the dimension of the eigenspace. Oops. That corresponds to the eigenvalue. So in this case, your eigenvalue has algebraic multiplicity 3. It has geometric multiplicity 1, because there's only one vector in my basis. Okay. The relationship between the two is that your algebraic multiplicity is always at least as big as your geometric multiplicity. Always. They have to be equal. For every single eigenvalue, they have to be equal in order to be able to diagonalize. So what we can conclude in this case is that C is not diagonalizable. Some books refer to such a matrix as defective. Yes. Say that again. Why? Lambda equals 5 has algebraic multiplicity 3 and geometric multiplicity 1. They're not equal. They have to be equal for every single eigenvalue. Yeah. Yeah.
So if the algebraic's greater, it doesn't work.
It doesn't work, right? Yeah, they have to be, the algebraic multiplicity for every single eigenvalue has to equal the geometric multiplicity every single time. Okay. All right. So what gives us a nice method for checking this is if you have distinct eigenvalues, then you always get a diagonalizable matrix. So you only have to worry about it when you start getting repeated eigenvalues. Okay? You only have to worry about it when the eigenvalues start repeating. If they don't repeat, then the eigenvectors are always linearly independent. Okay? Always. All right? So let's see why. Remember, what we have to show for linear independence is that the only linear combination that gives you the zero vector is 0. Right? So if you start with C1 V1 plus C2 V2 plus Cn Vn equals 0. If we start with that, actually, I should have, it doesn't matter. Another way to do that is that if one of these is not 0, then I can write one of them as a linear combination of the others, right? Okay. So let's say I could write my Vn, let's say my Cn is not 0. Let's say we can write Vn as C1 V1 plus C2 V2 out to Cn Vn minus 1. Okay. Multiply both sides by A. Oops. If I could put the A in there. And multiply both sides by, say, lambda n. Oops. What do these two these two left-hand sides? What's true about those two left-hand sides? They're both the same, aren't they? If it's eigenvectors, right? So if I subtract, and this one I could replace with lambda 1 v1. This one I could replace with lambda 2 v2 and all the way down, right? So when you subtract, we would get 0 equals, I can factor out that C1. I would have lambda 1 minus lambda n v1. I'd have a C2 lambda 2 minus lambda n v2 all the way out. And get this subtraction. Now, what did we end up doing here? I started with a linear combination of basically n vectors here, I've reduced it to n minus 1, didn't I? Now, eventually I would get down to one vector, which is certainly going to be linearly independent by itself. So I would have to have my C1 would be 0, and then I could work my way back up again. So this is, I'm going to stop here because of the fact that I don't want to go through the rest of the proof, and I want to chat about the corollary here in a second. The idea behind this is that if I start with this eigenvectors, there has to be a minimum set of them being linearly independent. And so we're just reducing down to that minimum set. So in any event, the theorem is still true. I'm sorry I didn't get all the way through it. The corollary is that a matrix with n distinct eigenvalues is diagonalizable. So looking at this last example that we have at the bottom, how do we find eigenvalues of triangular matrices again? This is the diagonal entries, right? Are they distinct? Yeah, so this one is lambda equals 3, 5, negative 5, and 4 are the eigenvalues. Since they're distinct, we know that A is diagonalizable. Okay? Say that again. You have to check in that case. You can have, if you have distinct eigenvalues, it guarantees that it is diagonalizable. If you have repeated eigenvalues, it may or may not be. Okay. We saw an example where we had a repeated eigenvalue and it was, and we saw another example where it wasn't. Okay. So it depends on the matrix, so you have to check it. All right, so that's the last thing we're going to do. I know there's stuff with linear transformations at the end. Remember, we talked about the whole point of doing, or not the whole point, but the goal of linear transformations was to replace the linear transformation with matrix multiplication. So you can also talk about diagonalizing linear transformations as well by diagonalizing the matrix associated with it. That was what the end of it is. All right, so final is on Friday. I will post some review problems over eigenvalues and eigenvector stuff.
Wednesday.
Try it. What did I say?
Friday.
Oh. Wednesday, yes. Final is Wednesday at 8. My apologies. Final is Wednesday at 8. I will post review problems over eigenvalues and eigenvectors. I will also go back and post blank copies of your exams from the semester and tell you what problems to focus on from those for studying for the review part.
When you
Am I doing that? I'll do that this morning.
You should do it right now.
I'm not going to do it right now. I have another class. But I will do it. All right. So I'll get that taken care of. I'll email when I get that done for you. All right? I'll be around Monday and Tuesday as well for questions. So feel free to stop by. Otherwise, have a good one. What's that? Oh, well, great. Thank you. Yeah.